Assalamu alaikum. My name is Ahmed Bokhari, and this is my effort to make sure that everybody, wherever you are, should be able to revise, study, understand chemistry, and obviously enjoy it. This is my So the topic that I'll start with, and just to give you an idea of what my vision is for this particular stream, I want to make sure that starting today, for O levels at least, if you have your CIEs this June, I would like to focus on that specifically, and I would like to make sure that whatever you need to study, to practice, to revise, all that's going to be on the exam. I hope to cover all of that, and I hope to make sure that you understand it in a way that when you're tested at the exam, you're able to answer the question and are fully equipped to do that. Of course, I'll be taking your questions, and of course, I'll be providing you worksheets. You can access those at the end of the each stream. I will post some links in the description of the video, so you can obviously see that. All right, so let's start. Whenever you're trying to learn a new thing, obviously it comes with learning new ideas, new vocabulary, and today that vocabulary that we're going to start with is kinetic theory. It is a foundational topic for chemistry, and without understanding and fully accepting it, it is very difficult to move on with the ideas that we are going to share and discuss. Of course, it's a difficult topic because it tries to explain everything that we have. And again, when I say everything, I mean everything that is matter. I do not say that vacuum is made of this, I'm talking about matter. So here's the radical idea, and it is radical because people, when it started, people didn't really like it. So here's the idea. We say that everything is made of particles. And that is something that you might not accept. You might be like, wait a minute, how come we have these particles going on and all that? Just give me a minute. For some reason, this screen is not sharing. Yeah, you should see it now. Yeah. All right. So the primary idea we have is that everything, that's the first thing, everything is made of particles. Now, the word particle in itself, it simply means a small portion, a small part. And that's where it comes from. It's a part that is really, really small. So that's the first idea. Everything that is matter, everything that has mass, everything that has volume, it is made of these small particles. And that is a radical idea because people did spend a lot of time, maybe 2000 years, to fully accept that idea with evidence, of course. Now, the next idea is that these particles are not just there. These particles are moving all the time, which means that first of all, we are claiming that this glass screen and my body, they are made of things that are really, really same or similar. And second, they're saying they're not stationary. That mobile phone is not stationary. There are things in there that are in constant means that it doesn't stop. Random means that you cannot predict which side it's going to go. Motion. So these particles are there. There are small things in there that make everything, and they're moving all the time. And the movement is out of our control. It's random. We cannot predict what side it will go to, and we cannot stop it. It's constant, which means no matter what you do to that, it will move on and it will continue to move on. And the third main idea that kinetic theory builds its case on is that particles, these things, have forces of attraction. So not only are these particles moving randomly, they also attract each other between, I'm going to use this symbol for between them, which are affected by distances between them. Of course, when it comes to distance, this also implies some understanding of arrangement. Okay. So these are the three main ideas of kinetic theory. Let me review them. Everything is made of particles. These particles are in constant random motion, And that motion obviously is affected by the forces of attraction that they have, which depend on the distances between particles. Now, there are four main ideas here that you need to know, and everything that you're able to explain using kinetic theory and everything they're going to test you should be able to explain using these four ideas. Let me highlight them. The first keyword that we have is motion. That particles move and that affects their behavior and of course the behavior of that thing that they make. Whenever the word motion comes, there's the idea of kinetic energy. I'm going to raise KE for kinetic energy. And that is also something that is closely related to motion. I'll explain in a while. Then we are saying that there is forces of attraction. So the next keyword that we have is forces of attraction between particles. And the fourth and last keyword is distance. So every question that you have on the exam, especially, you should be able to explain using these four ideas. If you're able to do that, you understand this chapter. Okay? All right. So these are the four main keywords that we have. Now, what exactly are we trying to achieve here? What exactly are we trying to explain? So to get a scope of that, I'm going to take the next 20 minutes and explain, or in fact talk about things that are being the subject matter that we have for this. We'll come back to these four keywords, just highlight them, note them down somewhere. So the first thing that kinetic theory tries to explain is states of matter. This word states, sometimes we replace it with phase, and that is similar to this. We usually represent them in parentheses. So there is solid, liquid, and gas. For solid, we usually write bracket S, for liquid bracket L, and for gas bracket G. That is what we write with the chemical equations. You might have seen them. Now, how are these three things different? Solid, liquid, gas, they all have same mass. There is a cornerstone of modern chemistry, that law of conservation of mass, which says that mass is neither created nor destroyed. It just remains the way it is, which means that in chemical reactions, mass doesn't change. And that's very important, especially when we talk about rates of reaction and all that. That idea is tested over there. So make sure that you remember that mass doesn't change in a chemical reaction, but volume does. Volume is something that is different from these things. In fact, solids have a fixed volume. Liquids have a fixed volume. Now that is something many students are like, wait a minute, weren't liquids compressible and all that? I'll explain in a bit. And then gases, they don't have any fixed volume. You can take a gas, you can compress it, you can change its volume, you can expand it, and it will change its volume as well. Doesn't happen with liquid. You buy, let's suppose you want to buy soda, and a half-liter bottle is a half-liter bottle. You can't take that half liter and try to squeeze it somehow and make just one glass out of that whole soda. You can't. All right, it's not compressible. And there are three main effects of this idea, the volume. Number one, density. Density is how many particles or how much mass you have in a certain volume. So you fix the volume. Let's suppose you might be like, okay, one glass of that thing, one glass of solid, one glass of liquid, one glass of gas. You might fix that to be 1 decimeter cube. So that is the idea that we usually work with in the lab, that 1 decimeter cube is something you can easily work with. So for volume, we keep dense decimeter cubes, sometimes centimeter cubes. Now that is the volume that we have fixed. Now how much mass you put in depends on the material you have. Now for solids, you can put a large amount of material just in that whatever volume you take. So this density is relatively high for solids. For liquids, the density isn't that much. And for gases, it's really, really low. Okay, so it's high in solids, it's low in gases. Okay, fluidity. Fluidity is the idea that things, do they flow or not? Now, obviously they're both liquid and gas, they make fluids. So this flows, this flows. But solids do not flow, they are not fluids. Last one, compressibility. Can you compress them? Okay, solids, you can't compress them. Liquids, you can't compress them. There are some liquids that we can compress, but to a very, very minor effect, maybe 0.01%. That doesn't really count. So we can't compress them. And gases, we can compress them all the time. We use it whenever we're using a compressor in a fridge, in an AC, in petrol stations, wherever we use gas, or you get it in natural gas resources and all that. We compress it all the time. We change their volume, and we are able to do that using gas laws. I'll talk about gas laws in a bit. So this is the first thing that kinetic theory tries to explain: the behavior of solid, liquid, gas, and all these things. There are basically 12 things here, 12 behavior that kinetic theory should be able to explain, and you should be able to explain the same. Okay, next thing is, do these states change from one to another? It turns out they do, right? Now, what does it mean to compress something? Mohammed, it means that you're squeezing it so that the particles, in fact, I'll try to explain without the particles. You squeeze it so that it has a smaller size for the same mass. All right. Now the next thing is, do these states change from one to another? And turns out they do. So for example, this one over here, the three states you have, this is a very interesting diagram here. We have solids, and forget about the little balls that we have here. Solids change to liquid, liquids changes to gas, and these processes have a name. When solid goes to liquid, that's melting. When it goes back, it's freezing. When liquid goes to gas, that's boiling. But there's another one we know, that is evaporation. That's another one. Similarly, gas going back is condensation. And then solid directly changing to gas is sublimation. Now gas going back is deposition, but in O level, especially the exams and all that, they are not going to use that word. So we will refrain from it again. So it is sublimation. All right, direct changing from solid to gas is sublimation. In 1 or 2 marks, they might ask you to define it. So it's when a solid directly, the word directly is important here. Evaporation and boiling are different. Why are they different? What exactly is there? So evaporation happens only at the surface. Boiling happens throughout the liquid. Evaporation happens at all temperatures below boiling point. They do ask about this in the MCQs, that if you have a liquid, let's suppose you have a liquid, it's not boiling at room temperature. That means its boiling point is above room temperature. But let's suppose you put it in boiling water. Okay, now it suddenly starts to boil. Why is that? That is not because boiling water has a boiling point of 100 and this thing also has a boiling point of 100. No, it means that either its boiling point is 100 or below 100, because it has already reached 100 degrees Celsius, so it must boil already, right? So if it wasn't boiling at room temperature, but it is boiling at 100, that means that the boiling point is somewhere in there, because you just put it in boiling water, which was at 100. So that is something they test in the exam. Okay, so evaporation and boiling, the differences. The two main differences are evaporation happens at the surface, boiling happens throughout the liquid. And second, evaporation happens at all temperatures below the boiling point, but boiling happens exactly at one temperature for any pure thing. That's a new word here, pure. I will explain what that is. Kinetic theory, in fact, does that. The third thing that kinetic theory tries to explain is what happens when you heat things. Okay, so solid is solid. As long as it's not melting, it's solid. Doesn't matter what the temperature is. If it starts melting, it's liquid, and that liquid stays the way it is until it starts to boil, and that is gas. And as far as O levels or IGCSE is concerned, we are restricting ourselves to these three gases, these three phases. The third thing that kinetic theory tries to explain is what happens while they're changing that state. So let's see. You can do it for example, if you take a glass of water, you can go home, put it in a freezer, record the temperature before you do it. Now take it out after 5 minutes, record the temperature again, put it back, record it after 5 minutes, take the temperature, put it back. Keep on doing that. You will actually end up with a table. You will have time, the intervals, and the temperature reading that you have. And you will start, if you make a graph out of it, of cooling it or heating it, you will get a curve that is remarkably similar to the one that I'm going to show you. This is called a heating curve, or the other one is called a cooling curve. Now, if you look closely, what's happening here? We have a solid on this left side. I'm talking about the heating curve here, this one. This is heating curve. Now, the solid is there and the temperature is rising. How do I know temperature is rising? Because the value is going up. On the graph, the temperature is on the y-axis, the value is going up. Then something happens, and it at a certain temperature, the value stops going up. It just stays where it is. And if you do that experiment in the lab or at home, you will see that you will have some solid that has melted and some solid that is still in the process of melting. So you will have both solid and liquid state here. The temperature will not rise, you will have both solid and liquid. And when all the solid has converted to liquid, that's important, all the solid is melted, then the temperature will start to rise. So how would you know that all of it is melted? The temperature will start to rise. Now this temperature is called melting point. I'm writing MP, but you can't do that in your exam. You will have to write the whole melting point word. Similarly, the liquid starts to heat up, you're heating it, and there is evaporation going to happen. Notice that this is the range of evaporation from the melting point all the way up to boiling point. Evaporation is going to happen in all of that. And then at this temperature, you are going to get, which I'm going to call boiling point. Again, you have to write the whole word if you're going to use it. You will see that it has both the, sorry about that, you have both the liquid and the gas state at that temperature. So it's going to be both, not one. Okay. Now that's the way it is. And there are two main ideas here. Number one, temperature changes here, here, here. If you're cooling it, temperature changes here, here, and here. That is the reason, that's the region in which temperature is changing. Then there is a region where the temperature does not change at all. For example, this one, or this one, or this one, or this one. You will notice that these are the regions in which temperature is not changing. And not just that, the second region is longer in terms of time compared to the first one. You're heating at the same rate. Why is it that liquid takes longer to convert to gas than solid takes to convert to liquid? Kinetic theory tries to answer that. So three main physical phenomena that you should be able to explain using just 4 keywords. That's remarkable. That's the power of kinetic theory. And in the exam, they expect you to be able to do that. How do they ask you to do that? In the exam, they will say, describe. And when they say describe, they're asking you to just tell me what you see on the graph, what you see over here, what you see over here. When they say state, that is all they're asking you. All of this. This is something that you can easily observe in the lab, that you can easily observe in life. It has nothing to do with kinetic theory, right? Kinetic theory comes in when they ask you to explain. Because in the exam, if they ask you to explain something, you have to give a reason. And that reason is coming from kinetic theory. And again, you will use 4 keywords for that. So let's see what exactly is the difference according to kinetic theory in solid, liquid, and gas. If you look at this diagram, these balls, they're supposed to show different particles. Remember, kinetic theory said things are made of particles. So these small balls, they are the particles. We had keywords. What were they? Particles are in constant random motion. So the motion is the first keyword. Then they have distances between them. That's the second keyword, which are affecting the forces of attraction between them. And with motion, I related it to kinetic energy. So that was the 4th keyword. There is a 5th idea that examiners sometimes asks you about, which is arrangement of things. So I'm going to write all of that. Solid, liquid, gas, and the keywords were distance. Of course, distance affects the arrangement. Then forces, that was the second keyword. Motion, third keyword, and kinetic energy. Okay. Here's what kinetic energy says. Kinetic theory says. And again, we will try to explain using these words when we go back to those 3 phenomena. Number 1, and I'm going to keep it even simple. I'm going to just talk about solid or gas. I'm going to ignore liquid. So let's talk about solid. Go back to the diagram. Notice that these balls, these blue ones, they're really, really close to each other, which means that the distances between them are low, small. Now, what about gas? The particles, if you notice, they're very far away compared to that one. They're almost touching, and over here in gas, they're not, they're far away. So in gases, the distances are large, they're high. Okay. Arrangement. Again, borrowing from the diagram, in this solid, the arrangement is fixed. You notice that this is very regular pattern. This is a regular pattern going on. It's an array that goes on in all directions in 3 dimensions. But that's not the case in gas. In fact, in gas, what we see is these long trails. These trails are supposed to show that particles are moving with rapidly. And over here in the liquid one, you do see some trails, but not as long as this one. They are over there in the gases, they're like comets moving around all the time. So kinetic theory says that the arrangement in solid is regular. The word regular means there's a pattern. It is fixed and there's a pattern. But in gases, there's absolutely no arrangement. It is not fixed. Don't say random, because these are all random. That's one of the main key ideas of kinetic theory. So don't say it's random. There is no arrangement. Okay, forces. Now the kinetic theory, of course, we cannot show forces over there, but it says that the forces there are strong in solid, but forces in gas are weak. Okay. Motion. We use a few keywords for them. So we say that in solid, particles are vibrating. Vibration happens when something is fixed to its place, just moving, nudging to one side and another, but overall fixed to its place. In liquid, we say they're sliding, and in gas, we say they are free or rapidly moving. That's the motion. Don't say random. It's random in all 3. Now, kinetic energy. We say that if something is moving more, it has more kinetic energy. That's the idea of kinetic energy. It's the energy of moving things. So in gas particle, they're rapidly moving, so it is high, and in solid, it is low. Now I want you to pay attention to this table. Look at gas, and then look at solid, and tell me, don't you see exact opposites? Gas is exactly opposite of solid. So what's liquid? Just the transition. Liquid is just in the middle, and gas and solid are 2 extremes of this spectrum. Which means that if you understand just one of them, you can easily convert it to the other ones. If you just understand that gas particles are free and solid is opposite to that, you know that solid particles are confined to their spaces. If gas particles are moving randomly and in all directions and rapidly, then solid, which is the opposite of that, they're not moving at all. They're very low. There's very low movement. Of course they're moving, but there's very little movement. That's vibrations. So if you understand just gas, you understand the rest, because that's just a spectrum going away from the gas behavior. Okay, and there are no black and white things here. There is a spectrum. So arrangement slowly changes to not fixed. Forces are weak in this gas and they become stronger, and then kinetic energy goes from low to high. Now here's an interesting thing. The forces are exact opposite of distance. And I told you in the beginning, distances affect forces. Which means that if you have strong forces, the particles are not going randomly away. They're close together. Okay? So forces are opposite of distances. But if you notice, if the distance is higher, motion is also very fast. Kinetic energy is higher. Now this does not mean that kinetic energy increases the distance, or if you increase the distance somehow they're producing kinetic energy. No. What it means is, if they have more kinetic energy, they're able to move more. If they're able to move more, they're able to move far. That's it. That if you give them more kinetic energy, they're able to go further away. That's it. So kinetic energy says this, but let's put these claims to test. We should be able to explain whatever 3 phenomena we talked about using these 4 keywords: distance, forces, motion. Okay? Distance, forces, motion. Remember that. Now let's go back. Why, and this is what the examiner will ask, explain. Okay? So whenever they say explain, they don't say why. When they say explain, you have to give a reason that comes from kinetic theory, and you have to use the 3 keywords. Not all of them, but at least from there. So explain why solids have fixed volume. So go back to what volume is. Volume is the space taken by these things. The distances between them will determine that. And in solids, particles are already so close together. So now we have formulated the answer that in solids, particles, the distances between particles are already very small. It's not possible to reduce them anymore. So their volume is fixed. Okay. Why are they not fixed in gas? Why is the volume not fixed in gas? Same. In gas, the distances are large. Particles can be brought together without changing state. So gas is compressible. Gas has volume that changes. Why is the density in solid high? Or explain why the density in solid is high. Really simple. In solid, you put more particles close together. That's the idea of distance. Because there are strong forces pulling them there. So the particles are being pushed close together by these strong forces. Of course, you're going to get more particles in the same space. Why do gases have, explain why gases have low density? Because in gases, particles have large distances between them. So there's few of them in the same volume. So if you have less mass, you have less density. Okay. Why are gases able to flow that rapidly or more than liquids? The forces allow particles to go away because the forces are weak in gas. In liquid, they're still flowing because the forces are still weak. In solids, the forces are very strong. They're not allowing them to go away. So you see, all of these behaviors we are able to explain using just 3 ideas. That's it. Just 3 ideas. Okay. What's happening here? From solid to liquid to gas, the only difference is how far the particles are. Technically, that is the key difference that determines everything else. If they're very close together, they affect forces, they make them strong, the particles remain in their fixed position, they vibrate because they're not able to move that far away, and the solid begets. In liquids, particles have weaker forces, the distances are large, they flow around, they move around because of that. All the behavior comes from that. And in gas, the particles have very weak forces, so obviously they can go further away and they have high kinetic energy because of that. Okay? Yes, I will try to save this video. If you have any question, feel free to type them in here. So this is the main idea here. Now let's try to explain what's happening to the heating curve or the cooling curve. And for that, we will have to understand how kinetic energy affects these things. So I'm going to take a 1-minute break over here and then we'll come back and we'll talk about what energy does to things. Okay? All right. So how does energy affect things? How does energy affect these particles? So here's the thing. Kinetic theory says that when you give energy to things, and I'm talking about heat energy because that's the easiest way of transferring energy to these things, that energy can be transformed. Remember, law of conservation of energy. Energy can neither be created nor destroyed, but it goes from one form to another. So this energy goes into the things and it can either go and be used to convert to their kinetic energy. So when things have more kinetic energy, remember, they move more. So either it will make them move more, or if it doesn't do that, then it will convert to a form of potential energy, and that will overcome or break down the forces between them. So 2 things can't happen at once. Either the energy will go and change the kinetic energy of things, increase or decrease it, and that means that you will see some effect based on that. Or it will go and overcome the forces that you have there. Now, how does this manifest itself in real life? The kinetic energy, when that changes, you will see a change in temperature. So the temperature changes because of this. Why? Because remember, temperature is a measure of average, I'm writing AVG for that, kinetic energy of all particles. Which means if you increase the kinetic energy of all particles, temperature is going to go up. And if you decrease the kinetic energy of those particles, the temperature is going to go down. Now, what happens when you overcome forces? State changes. So, kinetic theory says that energy can do two things. Either it will raise the temperature of substances, or it will change the state of substances. So either the temperature changes or the state changes. Now what's happening at the particle level? When the temperature changes, energy is converted to kinetic energy. And when it overcomes the forces, that is state change. Now if you study physics, you might remember a word, latent heat. This energy over here, that is latent heat. It is not affecting their kinetic energy. It's not changing the temperature. So of course, it's not showing up on the thermometer. But latent heat is there because energy is used to overcome the forces. Now, if the temperature changes, you can actually measure how much energy goes in by this formula. Energy is equal to mc delta T. And in calorimetry, sometimes they ask us to do this. In IGCSE, there is sometimes a question in paper 6 for this, but in O levels, they haven't really used this idea that much. In a couple of MCQs, sure, but those could be done using ratio method as well. And latent heat, of course, you can measure it by using the formula Q equals ml, which is pretty straightforward formula coming from ratios again. So here's the thing, the kinetic energy will affect temperature. So if you're seeing, now it goes the other way around. If you're seeing a change in temperature, kinetic energy is increasing. If you are seeing a change in state, forces are overcome. Now let's go back using this idea. Remember this and try to explain this curve, the heating curve and the cooling curve. Now the yellow portion is where the temperature is changing. Temperature is changing, kinetic energy is changing, which means when you heat them, particles move faster. But the solid remains solid, the liquid remains liquid, the boiling part remains, the gas remains gas. The pink portion over here is when the state is changing. And that is when forces are overcome. What about kinetic energy? No effect. All the energy is used to overcome forces. So kinetic energy won't change. Temperature won't change. That's a very powerful idea. Explain why temperature does not change when a substance is melting. Because all the energy that you have provided is being used to overcome the forces. Kinetic energy doesn't change, that's it. Okay, why does it take more time to boil than to melt? Because you need much more kinetic energy in a gas than you need in a liquid compared to solid. Solid में तो है ही कोई नहीं. It's depleted of all the kinetic energy that you have. It has very little kinetic energy. So you give it a little more and it can easily convert to liquid. But to convert it to gas, when every particle is free from every other one and the forces are negligible, you need substantial amount of kinetic energy and you have to supply all of that, and forces have to be completely broken, which is why you have to give them much more energy. It takes much more time. Again, I'm able to explain all of that using just force, distance, and motion of particles. And you should be able to do the same. Alright, now let's talk about what happens in evaporation. This is the last thing today. When particles evaporate, not all of them do. Right? When a liquid evaporates, not all the particles do. Why is that? Why is it that in boiling all of them are evaporating, but in evaporation, not all of them do? Now, the exact reason of why things evaporate, we don't really need to go into that for O levels or IGCSE. But just remember that evaporation is when a few particles who have much higher energy are able to escape and become a gas. But the particles boil when all of them have enough kinetic energy to become a gas. Okay, so in that sense, these evaporating particles, they're like the elite at the highest level of their energy. And they are able to escape because they have enough energy already, but there are few of them who do. When it comes to boiling, you're giving energy to all of them. And they are all able to eventually change to gas. So they need a certain level of energy to overcome the forces, and if they already have that in a liquid, they will escape. And if they don't, they will stay as a liquid until all of them have that energy and they're able to escape when all the forces are overcome. Okay, and that is the power of just 3 words of kinetic energy. And remember this, I can't stress this enough. In your answers, you have to refer to this if they ask you to explain the reasons come from kinetic theory. All right, so that was it. I hope you understand it. If you have any questions, I'm here. Let me know. All right, thank you so much. See you tomorrow at 8. Allah Hafiz.